So my name's Kevlin Henney. I've got an interest in the detail, the small picture, if you like. I with Trisha G last year, we finished 97 Things Every Java Programmer Should Know. 10 years before that, there was my 97 Things Every Programmer Should Know that gathered together the ideas, thoughts, and perspectives of many people. So that's the kind of the code-centric detail, but there's another perspective I want to offer you, which I happen to have ended up in books as well. I have a long-standing interest in design patterns, and people often misunderstand them, but co-authored these books, Pattern-Oriented Software Architecture, and the nature of these books is to really dive in, particularly the fifth one, dive into kind of the theory of patterns and stuff like that. That might not be of interest to you, but it's kind of a the reason Frank and I and Doug wrote this was very much, let's put all the stuff that we kind of think about in terms of architecture and design and so on in one place, so that when people ask us things, we can go, oh, look, there it is. There's a book. Now, the thing that's obviously relevant here today is the word architecture. We are talking architecture today, and I wanted to explore our alternative sources of inspiration, and I often quote from different disciplines. I find that it's very helpful to truly understand what we do, particularly in software, which is very abstract, by taking inspiration from other sources. Now, we're not alone in doing this. This is a very common thing. I find this as a standard thing in life. Professions look at each other and say, we should be like this, or let's take that idea from that discipline. We're not unique in this from software. I found that some software people think that they're unique in this. I think that's a very common way that people view this. There is certainly something special about software, but using the architecture metaphor absolutely is not unique. If you think software people are special in this, using the engineering metaphor, again, not unique. Lots of people do this. It turns out all the professions do this to a greater or lesser extent. And this is a natural thing. This is a very human thing. And there's actually a book that was published 40 years ago, 1980, in fact, Metaphors We Live by George Lakoff and Mark Johnson, where they explored the idea of metaphor, and not just the way that people tend to think of metaphor as being something poetic. They talk about metaphor as actually shaping our thoughts, particularly when we are talking about things that are relatively abstract. The more real or physical or kickable that something is, then the more likely it is the basis for our ideas. The more abstract something is, the more removed from something that is kickable and physical, the more likely we are to use it by metaphor. And we do this everywhere. It informs our use of prepositions, whether we say on or at or in, and about something. It influences our languages, our spoken languages, not just obviously it influences each one slightly differently. There is also the idea when we deal with abstract concepts, things like time. How do we talk about time? Relationships, reasoning, thinking. What are the terms we use for that? So the idea is that the point here is there's this observation: metaphor is pervasive in everyday life, not just in language, but in thought and action. The essence of metaphor is understanding, experiencing one kind of thing in terms of another. And we do this everywhere. And we can see, certainly in software, all of our terminology is metaphor based. So, if you're probably looking at a screen that has windows on it. Okay, well, window is a metaphor. Window provides its own vocabulary. It comes with the idea of opening and closing, or seeing through something. It gives us the vocabulary of view. When we talk about model, view, controller, where does the view come from? It's not just that we are looking at something, it's that it is a window provides a view. This is the historical perspective here. We work, my laptop has a desktop. My laptop is actually on a desktop, so we have a correspondence there. We talk about file systems. Those are not files, but you can read and write to a file. all of these ideas, all of our language, the language of networks, sockets, it's all metaphor. Okay, so pretty much everything that you find in a piece of code is based in some way on metaphor. Now, it doesn't mean they're always good, but it does mean that what we're trying to do is, in terms of motivation, and I put this in an article last year on technical debt when I explored the metaphor idea. Sometimes because we want to show something familiar from an unfamiliar angle, as in poetry, but sometimes because we want to show something unfamiliar or abstract in a more familiar light, as in software. We use metaphor all over the place. Now, the most obvious one with software architecture is the metaphor of architecture. There's a lot that we can rely on. That doesn't mean that it's perfect, and let me be very clear. Sometimes people talk about, oh, that's not a good metaphor, and they criticize a metaphor because it's not perfect. While there are reasons we might want to criticize a metaphor, you can never criticize a metaphor because it's not perfect. That's the whole point of a metaphor. If it were perfect, then it would be identity. Metaphor is not identity. Okay, there's a very subtle difference. What we're doing is we're saying there are some things in this idea that translate to this idea, and I'm going to talk in terms of this idea to give you an understanding, an alternative viewpoint on this idea. This also means this has to be familiar. Okay, it's no use me choosing a metaphor of chemical process engineering, because it turns out that most people, unless you're a chemical process engineer, don't know what that is. But if I choose architecture, well, we all live in buildings. We've all seen, we have ideas. Doesn't mean our ideas are right, but we certainly have opinions about it. And the idea of architecture offers us certain views. So what I'm going to look at in this talk is certainly I'm going to look at architecture, the original architecture, but I also want to borrow ideas and inspirations from art. I want to borrow them from writing, a couple of thoughts from science. Just draw in what can we, when developing a system, when we are thinking about its architecture, where can we draw inspiration and alternative perspectives from? Doesn't mean we have to take everything, but anything that we can take is useful. So let me start with this book by Matthew Frederick, 101 Things I Learned in Architecture School. This is actually about building architecture, and it is actually quite a lovely book. It's got high production values, and it has you normally have a drawing on one page and a quote or description of something on the opposing page. And there's a lot of really good ideas in here, and probably about half of them you can see the inspiration. You can immediately go, wait a minute, I'm familiar with this idea. I've seen this in software, or this idea is something in software we could learn from. In other cases, you go, no, that's really different to what we do, and I don't see a translation. But about half the advice applies to any design-based discipline. The number of times I recommended this book, I have lost count, but I have certainly had people who have if I had been on commission for selling this book, I think I would have made a reasonable amount of money. I think it's a lovely book. I even know of somebody who actually they bought it, and he bought it, and then his wife took it off him because his wife said, "Why are you looking at this? It's a book on architecture." She's actually an architect, so she found it really good and walked off with it. So he had to get a second copy for himself. So it clearly also has appeal to actual architects. But I want to start with a quote that is included here from the Finnish architect Eliel Saarinen. Always design a thing by considering it in its next larger context. This is really important. We have a very strong habit because of the idea of abstraction. We have a strong habit. What is abstraction? Abstraction is removing things. It's a very important tool in software. But sometimes we remove the wrong thing. Sometimes we remove something from consideration that should have been considered. Sometimes we don't really appreciate, we got focused on the technology, or we got focused on the new idea, and we go, oh yeah, this is great. And then we realize actually it's got to integrate in a completely different environment. We need to understand the environment. Many people are applying techniques. Perhaps they have watched videos of talks or read blogs about some of the stuff that's happening at scale with people like Google or Facebook or whatever. And they think, yeah, we're going to borrow that idea into our organization. The problem is that's not your context. It doesn't mean that the ideas are good or bad. It just means that's not your context. Maybe they don't fit. The quality of a design is not determined by if it's good internally. It's not just that, it's whether it fits with the world around it. And that world can sometimes raise questions, questions of ethics, questions of security, questions of performance and usability. So the interesting thing here is that I have certainly had the experience over many years of architects who effectively try and close off too much from the business context, the legacy context, the context of what the developers actually know. That maybe they make a technology choice, but we don't have the skills in-house or the time to acquire the skills. Or we're choosing something that really is a piece of over-design. There's an idea here as well that sometimes when we're not sure about things, we will try to generalize. And sometimes we regard generalization as a value. But another observation in this book, the more specific a design idea is, the greater its appeal is likely to be. Of course, we can generalize things, but we are, most of the time, we seem to be forever lost in a world of infrastructure and frameworks. And sometimes, I'm not a JavaScript developer, but sometimes I look at the amount of how deep the technology stack for basic web development is, that you kind of forget that most of that is actually not necessary. That in many cases there is a simpler solution, but what you've ended up with is a generalized framework for everything. And that adds complexity. It's not to say that you don't want to use it. It's not to say that it's always wrong. But if you want to end up with a good design, something that is reusable, don't start by trying to generalize it. Start by trying to make it specific. People don't have general problems. They have specific problems. They don't want their system to be general. They want their system to be specific. So there's this constant balance. Now, let's look to the world of writing and the performing arts. Shakespeare. I'm going to borrow from an observation from Hamlet. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. This is important because when people try to generalize, there is the danger of, oh, maybe this situation will happen, maybe that situation will happen. They're generalizing and they're trying to predict the future. Invariably, they are wrong. The future will always surprise us. The future will either be more boring or more exciting or somewhere else other than what we have handled. The term, sometimes I hear it a little less these days, which I think is good, but maybe we've just moved on to using other words. People used to talk about future-proofing their code and creating a future-proofed architecture. This architecture is going to handle all of the changes. I have been in software development long enough to know that almost every attempt at generalizing has pretty much failed. Premature generalization has at some level failed. So what is the limit? When people say, oh, we're going to evaluate and do all of these alternative things, it depends on how good your imagination is. This is the curious thing, is the more imagination you have, the longer you will spend trying to generalize because you're imagining all of these possibilities. So rather than playing that game, just recognize when to stop. As William Gibson, again, let's refer back to fiction, that which is over-designed, which is too highly specific, anticipates the outcome. You're trying to second guess the future. And the anticipation of outcome guarantees, if not failure, the absence of grace, that your system will be clumsy. So a lot of attempts at future proofing are based on just pure speculation. Now, speculation is a very powerful tool that humans have, our ability to imagine a future. But the problem is that we end up trying to kind of encode that and make our architecture account for these futures that we have never visited. And you know what? Maybe they happen. The chances are they don't, because there are things that we did not imagine. Having lived through all of this, I remember all of the UI frameworks in the 1990s that were supposed to allow you to target any platform's UI without having to actually rewrite the code. Oh, I'm writing for Mac, I'm writing for X Windows, I'm writing for MS Windows. They were all general, and not a single one of them was able to handle the shift to touch screens, the shift to different technologies. So for example, virtualization, Java, .NET in their original form, not a single one of them was able to handle the change in screen dimensions. Oh yeah, they could generalize from 640 to 800, but not much beyond that. And the change in screen ratios, the mobile revolution, not a single one of these frameworks that predicted the future survived. Likewise, a lot of the container style UI designs that were used for the web in the 2000s, again, very few of those even made it onto mobile or survived in a way that was useful. Most attempts at trying to second guess the future will fail. So build something specific for now and then generalize based on that experience. And that's a really important point. So let's talk about patterns. Let's talk about this book, Timeless Way of Building, from Christopher Alexander. That's where patterns came from. Patterns came from building the built environment, real architecture. Now, this book was published in 1979, and it was a culmination of the work of Alexander and his team in the 1970s. Now, I don't specifically want to talk about patterns here, even though I'm citing a patterns book. I want to talk about the fact that this is one of the books where I really learned about the value of context-specific design. The idea that working in one language versus one programming language versus another, don't try and translate don't try and take all of the ideas from one language to another. Otherwise, you're going to end up programming. If you've learned Java, then you're going to end up programming. Let's say you decide, let's try Haskell. You're going to end up using a Java style in your Haskell. That's not particularly useful. Likewise, using design styles from C when you're working in C++. These are not successful strategies. Treating your Python code as if it were C#. These don't translate. They are context specific. What is defined as good in each environment changes. But it's also broader. If you are dealing with multi-threading, if you're dealing with true parallelism, then it turns out that there are a number of guidelines that you need to follow. But they don't make sense if you are working in a language that is strictly sequential. There's no need to take on those ideas and those idioms of design, because they don't solve a problem that you have. Likewise, there are a number of techniques that work well for the network, but are clumsy if you are programming within a single address space. But likewise, there are other techniques that if you're working, or principles that if you're working in a single address space, they don't scale at all to a distribution. So the value of context, but there's something else here. There is an idea of design that is valuable, hidden inside patterns. So often when I talk to people about patterns, it's not, hey, look, here's a book that somebody wrote, 4 guys wrote in the early 1990s that have 23 ideas that you find commonly across frameworks. No, that's not interesting. It is important, significant historically. There's a real idea here that people miss about patterns, that you are supposed to understand the context. There is a dialogue that you're having. We know that a pattern is an instruction of the general form, the context, the situation in which our design occurs, or the challenge that we're having. In fact, name the challenge in terms of conflicting forces. Sometimes we just call this the problem. What is the issue we're trying to resolve? And forces, that's very metaphorical. It's like we're being pushed one way and another. Hey, if I do this, it'll be faster, but if I do that, it'll be more maintainable. If I do it this way, then that is familiar. If I do it that way, there might be a performance benefit, but it's less familiar. If I do it this way, it'll be harder to update, but the performance is great. We're looking at this conflict. No such thing as a design solution that does not have to make trade-offs. And then configuration. Now, obviously, as software developers, we have an idea of what configuration means. It's not that. We're talking, Alexander is using the word configuration here simply to mean structure or solution. So the idea of, effectively, we're telling a story. It's a 3-act play. Here we are. This is our problem. Here is a solution. That also has consequences. But that is not that's not unique to a pattern. Actually, we can replace the word pattern here and replace it with the word design. There's some questions coming up in the stream about the streaming. I can say that at my end, the streaming is good, so it might be elsewhere in that case, because people are having different experiences of this one. So let's put it another way. Every design decision is an instruction of the general form: context, conflicting forces, configuration. We see a generalization of this if you come across architecture decision records from Michael Nygaard 10 years ago. Really good idea, becoming increasingly popular, ADRs. They follow this Alexander-style structure. It's a story. What we're trying to do is let people into our thinking and understand the rationale of our design decisions. But there's something else that Alexander is talking about here. How do we know that a design decision is good? We say that it is good whenever we can show it meets the following 2 empirical conditions. Now, this is an important idea. Also, by the way, as a general observation, Christopher Alexander did not say that a pattern is a thing that is good. He just said that a pattern is a thing that recurs in terms of design. And not all patterns, not all things that are repeat are necessarily good. Whereas in the software world, there tends to be a bias towards the assumption that the word pattern means good. And he's not saying that. He's saying there are patterns, and some of them are good and some of them are bad. Because we've confused ourselves a bit, we've ended up using more complex terminology. In the mid-90s, people came up with the term anti-pattern. It's like, no, there's a simpler term. It's called bad pattern. That's it. You know, Alexander was using language that a 5-year-old would be able to understand. He uses words like good and bad. So there's the question: how do we know when something's good? How do we know that a design decision is good? Is it purely subjective? Is it my opinion? And he said, no, there's 2 empirical conditions. First of all, the problem you're solving is real. Now, in one sense, this seems amazingly obvious, but I want you to think, how many times have you actually done something and then realized later that the problem that you were solving, it was imagined, it wasn't real? You've added complexity to the code. And I've certainly seen this in from architects in architecture documents and guidelines, people recommending things just in case this happens, or it solves this problem. And then you pause a moment and you think, do we have that problem? No, we don't. That's an imagined problem. Now, that's not to say it won't happen. And of course, if you have all the time in the world, then pay attention to it. But that's one of those futures that may not happen. There's a lot of other things that you do actually have to solve. So in other words, are we solving a real problem? Let's prioritize it according to that. If we have no problems, then let's solve imaginary problems. But if we do have some problems, let's prioritize it in terms of things that are real and being experienced now. This is an empirical question, okay? And then the really obvious one, the configuration solves the problem. Let me rephrase that for you. The solution solves the problem. The solution is a solution. How many times do people make recommendations or use techniques or introduce frameworks or separations in the architecture or particular architectural decisions and styles? The number of places that are, for example, adopting microservices when they don't need to. I'm not saying microservices are bad. They solve a very specific set of problems, and you can find out which ones they are by applying this filter. But when we do this, have we actually solved the problem, or do we just feel good? Have we just made the code more complex? Have we made it more obscure? There's a lot of people out there trying to do microservices because they want to break up monoliths because they think that it will help them do design. We've had this since the 1960s. Every decade, we invent a new paradigm or adopt a new paradigm for trying to solve the problem of large, unmanaged bodies of code. We had structured programming, we've had object orientation, we've had component-based development, we've had microservices. We had services and then we had microservices, but these days microservices are actually bigger than services used to be when people were talking about service-oriented architecture. The point is, if you are adopting microservices because you want to improve the quality of development because you don't think people are doing good decomposition, you know what? You've already got the tools. That's not a real problem. You've already got the tools to do that. And you'll probably find that you don't end up with an adequate solution. If, on the other hand, you are adopting microservices for reasons of updatability and distribution and replication and all of these other aspects, then you think you've come to the right place. So this is a really simple thing. And this is an empirical approach. And it's something we need to remind ourselves to do. Are we actually doing real stuff, or are we making the stuff up? Are we fooling ourselves? And the Nobel physicist, Richard Feynman, had this lovely way of putting it. Science is what we have learned about how not to fool ourselves about the way the world is. Remind yourself, actually experiment. Now, I've got a question from MP in the thread here, which is really interesting. Usually a problem in IT can have multiple solutions. Yes, even in the simplest cases. How do you know the chosen solution is the good one? Right, you don't. All I've offered you here is to know that it is good. I cannot tell you that it is the best, but you have a simple filter for finding out if it's not good. So the idea is there are multiple solutions. We may not find the best one first. We may not even find it second. But the point is, we won't be able to make any judgment on, is it any good at all? Don't worry about if it's the best. Is it any good at all until you've finished it? There is this idea. This is why we want to try and focus on building things in small steps, building things with iteration and feedback. You have to finish things. That's what you learn from. You learn by finishing things. Now, Neil Gaiman was talking specifically about writing here. He's a writer. But I find that this is generally true of any creative endeavor. Now, if we look to the world of screenwriting, there's another observation that comes from Robert McKee. He observed, if a plot works out exactly as you first planned, you're not working loosely enough to give room to your imagination and instincts. This is an interesting idea. Not that we often suffer from actually meeting our plans in software, but there is an interesting thought. It means that if we did end up delivering something and developing it according to an initial plan, then we probably missed learning something. We probably missed understanding something that is going to be useful and helpful to us later. The whole idea is that we should be paying attention continuously, not just in an initial phase. Architecture is not a phase that happens at the beginning of a project. Architecture is a continuous concern. And that means you've got to be paying attention to what you're doing. Now, this is a little bit disturbing if you come from a traditional project management background, because, as Matthew Frederick observes, properly gaining control of the design process tends to feel like one is losing control of the design process. What is happening is, instead of having a fixed plan that is temporally arranged, that this happens here, 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 and here, you have something that is much more dynamic, much more opportunistic, much more about paying attention. It doesn't mean that there is no plan. It just means your plans are fluid and your plans are filled with possibilities. And what you're looking for is, which possibility makes sense now? Which possibility should I look out for on the road ahead? And that's a really important idea. We are very bad at using the metaphor of, for example, the roadmap. I see architecture roadmaps and product roadmaps. And you know what? All of those roadmaps only ever have one road. To be honest, if you have only one road, you don't really need a map. That's the whole thing, exactly as MP said. A problem in IT can have multiple solutions. We don't know what is the best at this point. And indeed, the best at this point may change with time. Technology may change in a way that means that this year's best decision is not next year's best decision. It may change in a way that means last year's rejected solution is actually a really good one this year. It means that what we're dealing with is a continuous set of options. That's why it feels like we're losing control. But it brings to mind that there is this dynamic and emergent quality. And that's why, if you have the role of architect, the architect needs to be present. They need to be there. They need to be there all the time. If your architecture is owned by the team, it is collective, then the team needs to genuinely take that as a responsibility rather than not a responsibility. There's another observation from Andrei Nikolai. From a business perspective, you might usually hear it should support the business for X years. And we all know that nothing lasts forever and new ideas come out regularly. So I feel that what is best now could change in 2 years. And I think that's exactly right. The idea of what we mean by good is a function of time. It is not eternal. Whereas often the way that ideas of good are presented in software, they're presented as if they were forever. And I keep seeing we fall into this trap. Whereas if we just sort of say, yeah, this is the best for now. This is as good as it gets for now, but we might change our mind later. That's a really important idea. The roadmap we need to be thinking of is, driving by Google Maps. The traffic situation may change. Let's respond to that. Now, interestingly enough, Christopher Alexander, he was actually reasonably well known before the patent stuff. Notes on the Synthesis of Form, which is a difficult title to say, it was published in 1964. And I read this a number of years ago. And there's some really interesting ideas here. And you can see the origin of the patent idea. But he is talking generally, certainly from his experience in building architecture, but he is trying to generalize and say what the work of making things, the work of design in general. And he makes a number of observations and highlights a number of structures. People were very much into bubble and dot diagrams in the 1960s. In the 1970s, we started putting squares on things. But he says he's this idea of how systems interact, that we don't want things to be too tightly coupled, and this lovely observation that we can take in many ways about as architecture inspiration. We may therefore picture the process of form making as the action of a series of subsystems, all interlinked yet sufficiently free of one another to adjust independently in a feasible amount of time. Now, we can think of this in terms of the very structure, in terms of subsystems, components, services, classes, etc., of our system, and this idea of looseness of coupling to allow one thing to change, but relatively independently of other things. Okay, so it's not too tightly coupled, but it's also a description of process and how we do things, our very approach to stuff. As he says, it works because the cycles of correction and recorrection which occur during adaptation are restricted to one subsystem at a time. In other words, this is refactoring. This is reappraising your architecture. This is iterative refinement of what you're doing. This is exactly as you say, revisiting decisions after a couple of years or a few months to say, well, we had this and it was good, but is it still good? Or do we know more? Or has things changed? Now, let's go to the world of art, because there's a point here about process. The artist Austin Kleon has written a number of books, Show Your Work, Steal Like an Artist, and Keep Going, all of which are good. And I find them very inspirational, very helpful. And he talks about pace, because we are obsessed with bigger, better, faster, more in software. And the mantra, the old engineering mantra that was repopularized, unfortunately, by Facebook, move fast and break things. There's a whole idea, we have an obsession. People have reduced the complexity and subtlety of good agile development to an obsession with speed. Well, they call it velocity, but really it's speed. They're not concerned with direction. They seem to be concerned with rate and how much work are we doing. And there's an interesting thing here, is actually we should be doing the exact opposite. The work of software development is not typing. That is not the main bottleneck. That's not the thing that slows us down. The challenge is to understand what we are building. And the greater the understanding you have, the easier something becomes to build, because half the time you then work out what not to build. That's the real issue. So Austin Kleon says it's impossible to pay proper attention to your life if you are hurtling along at lightning speed. When your job is to see things other people don't, you have to slow down enough that you can actually look. That, when we think about our systems, that's the real trick. The job in software development is to see the things that other people cannot see or do not see. It's to see the subtleties or the ambiguities in the problem domain. It's to understand the little changes day by day could actually mount up to be a big change that's going to cause us a problem in a year. Unmanaged technical debt creeping up, okay? And just to notice that, you've got to slow down and look around. What are people actually doing rather than what do I think they're doing? An empirical approach. And it requires deliberation. It requires thinking. And it requires time. Now, time is an interesting thing, because this is another wonderful book on architecture by Stuart Brand, How Buildings Learn. It was published in the mid-90s. And on the cover, you see two images, two houses in each one. And the image on the left shows two houses in New Orleans in the mid-19th century. The image on the right shows the same two houses as they are nearly 150 years later. And you can see that they have responded and evolved. People tend to think of building architecture as being static. They think of architecture as, in that sense, timeless. They think of it as, and that's why they struggle to kind of, they draw the wrong lessons when they try and take architectural ideas into software. Now, architecture in buildings is always about change. It's just that they change over decades, not over months. That's the scale of the time is different. Okay, we live in an accelerated time scale in software, probably because we don't really have to worry too much about most of the physics. But there's another aspect here. In this book, he highlights, adapting a model from the architect Frank Duffy, he highlights a model that was later adopted and published as a patent by a friend of mine, Alan O'Callaghan. He called it time-ordered layering. And it was also popularized in Brian Foote and Joe Yoda's paper, Big Ball of Mud, shearing layers. And it's this idea that a building, a functional building, as opposed to a residential building, often has different rates of change. So the site is the most stable part of a building, where it is. It normally takes an earthquake to move that. The structure is the load-bearing structure that carries the weight. The pillars, the steel pillars that are hard to move. Okay, you can't move those easily because they hold up the building. And then we have the external skin, the facade of the building. Now, in office buildings in I think Duffy did his research originally in London, in office buildings of the kind of like the middle to late 20th century, the facade, the skin would change on a roughly 30-year cycle. And the services would change on a 5 to 15-year cycle. Services are lighting, air conditioning, cabling, and all of these things. And then the space plan is how you organize the space within it. And then the stuff, chairs and tables, these can move on a daily basis. So the idea is that we're looking at different orders of magnitude or different scales of time. And this idea is actually quite attractive in terms of understanding how to structure a system, to try and respect that you should depend on things that are more stable than you. Depend on if something is less stable and you have a higher level component depending on it, then extract a stable interface and make this a plugin, for example. And this idea of observing your architecture from the point of view of rate of change is very instructive, because not everything changes at the same rate. This helps us prioritize where should we put our effort. Let's say you need to put more effort into unit testing. You've decided that. Well, where should you start? Well, what changes most frequently? That's a good place to start. The stuff that doesn't change very often, it's not that it doesn't need that help. It's just that the more you change something, the more likely you are to get it wrong. So let's start there. But also, it turns out to have consequences for deployment and people's understanding. There is on multiple levels. Now, as it happens, on my desk, because I was just showing this to somebody the other day, I happen to have this rather good book, Adam Thornhill's Your Code as a Crime Scene. There's a lot of stuff in here on code analytics that is about rate of change. And that's the idea, is that we should be observing. This is the lesson we should be learning from these disciplines, is let's be observers and actually see what's changing. But there's another thing. Architecture is not just about structure and functionality. A lot of the time it's actually about living. So to borrow from Dick Gabriel, there is an observation here we often forget in software. There is an idea of habitability in buildings. And this actually also translates that when we talk about software architecture, people often talk very abstractly about the structure and the functionality, and they talk about other concerns like performance and so on. But the one thing we have to remember is that an architecture is a place where people live. That's why it exists in the real world. It's a place where people live and work. Okay, an office building is for working in, a home is for living in. The question we need to ask is not simply, are the services in the right place? Does it fulfill its basic function? But is it nice to live there? Is it nice to spend? A developer is spending their time, their days in a virtual environment, effectively, the code. What's it like to live in that code? This is what we want in software. Developers can feel at home. They can place their hands on any item without having to think deeply about where it is. If you like, habitability is a much more human observation about things that sometimes we try and talk about, but don't quite talk about in terms of things like, maintainability or stuff like that. It's actually a lot more concrete. So the philosopher Alfred North Whitehead observed that we think in generalities, but we live in detail. And this is the other aspect. There is the detail. And sometimes people divorce architecture from code. So let's just have a look at a couple of things from code, because what I want to do is I want to end today with some observations about the other end of the spectrum, the inspiration that we can actually get from things that are code. So I've got a little bit of Python here. I'm going to use the built-in Python sorting function. It's called sorted. I'm going to call it sort, and I'm going to do a simple test. I'm going to assert that the result of sorting is sorted. I need to write my own is sorted. There's a few other things that I could write here to confirm the behavior is good. If you're interested in that, go and see my blog, kevlinhenney.medium.com. I've written a lot of stuff on sorting over the last year or so. So I'm just going to keep this one kind of short. So what is the default implementation of Python sort? What's its performance? Well, it's an implementation of timsort, which is it uses timsort, which is a hybrid algorithm, and it has a typical performance of O n log n. Okay, big deal. You're thinking, yeah, this doesn't make any difference to me as an architect. I don't normally worry about my sorting algorithms, and because they've been commodified, they are available for you to use, and that's all good. Why does this matter? Well, let's do something a little more fun. I'm going to use an sorting algorithm called permutation sort, for which is actually really easy to do, basically a one-line implementation in Python. Permutation sort, what is the basis of permutation sort? Permutation sort is, instead of doing clever divide and conquer techniques, permutation sort simply iterates through all of the possible permutations, the combinations of the argument until it's sorted. The performance of this is absolutely terrible. It takes factorial time. Now, of course, This is what is known as an esoteric algorithm. It's not intended for production. So why is it useful? Because it allows us to talk about performance. And sometimes, and we're not very good at talking about performance, but or certain other characteristics of how a system runs. Sometimes people will say, well, you talk to people and say, oh, we don't have any performance requirements. I also talk to front-end developers and say, oh yeah, performance isn't, we don't need to worry about performance, or we don't have any performance requirements, or performance isn't a thing that we need to worry about, so therefore it's not part of our architectural concern. This is wrong. Performance is always an architectural concern. Whether it is also a problem is separate. You need to determine what it is. And how do we know what good performance is? People sometimes come out with numbers. They have no empirical backing for them. But what I'm doing with this example is simply demonstrating, okay, you're saying you don't have, performance isn't an issue, or rather, you're saying that you don't have any performance requirements. Okay, let's replace all the sorts in your code, every place where it might sort, because we often sort for presentation. But we also sort at the back end. Let's replace all of those with permutation sort, or replace some of our other code with things that are like permutation sort. Then suddenly you'll discover that people have performance requirements. You've created something that is functionally correct, but is dysfunctional in its execution over time. So there is an idea that somewhere between I don't care and permutation sort is where you start caring. That is the boundary. That's how you find your requirements. Now, I'm not suggesting you actually do this. It's a good thought experiment, but that's the point. As Shakespeare observed, this is the monstrosity in love, that the will is infinite. What you want to do is unbounded, but the execution confined. We are confined by hardware limits. We are confined on the network by the speed of light. We are confined in many ways. There are some things we will never optimize, and we need to have a proper conversation about that and appreciate those. The desire is boundless and the act is slave to limit. There's BOGO sort, which is one of the great sorts, great esoteric algorithms. There's variations of it. This is a relatively simple implementation, which basically randomly shuffles. What's interesting about this is it's actually not guaranteed to terminate. But if you're, but it may terminate very quickly. This has OMG kind of performance. Now, the point we're trying to highlight is that performance is always a consideration. It just might not yet be a problem. But to find the boundary of what is acceptable and not sometimes takes investigation. It is a process. It's not an answer that you present up front. It is also a detail. And sometimes people say, oh, we don't need to worry about algorithms. Sometimes this is one of those things that when I run workshops on architecture, I always ask people, what is architecture and what is not architecture? People often say, oh, implementation choices, those aren't architecture. Algorithms, those aren't architecture. Google is a company that is founded on algorithms. They are so profoundly architectural. They are huge. And the point here is that the way sometimes things can be details, but our question is that of judgment. And Robert Pirsig and Zen and the Art of Motorcycle Maintenance, which is a wonderful book, an inquiry into values, has this lovely bit where he's talking about the problem of a screw that is jammed in the motorcycle engine. He says, normally screws are so cheap and small and simple, you think of them as unimportant. But now as your quality awareness becomes stronger, you realize this one individual particular screw is neither cheap nor small nor unimportant. Right now, this screw is worth exactly the selling price of the whole motorcycle, because the motorcycle is actually valueless until you get the screw out. And with this re-evaluation of the screw comes a willingness to expand your knowledge of it. And this is how we need to be when we are considering software architecture. Details are not always unimportant, and that is a question of evaluation. So let's just look at a final esoteric algorithm and a couple of implementation choices that we might use to explore style. This is the sleep sort algorithm, which was discovered and published anonymously on 4chan in 2011. It might actually be the only good thing to ever come out of 4chan. And if we run it, it was originally written using Bash, but actually you can write it much more simply using just straight Bourne shell. And this is really interesting. I mean, you might be able to see what it's doing. It's a crazy piece of code. And it initially looks like it's linear, which is kind of cool. But there are other questions here. Now, the point here is I've done that as a process-based thing. I could re-implement this using threads. So this is some C++ that does it in threads. And actually, there's not a big deal except for the language syntax that's different between these two solutions. You know, one is in Bourne Shell and the other is in C++. The thread solution, because there's no communication involved, is very similar to the process-based solution. So there's no big distinction between the process-based paradigm and the thread-based paradigm for this problem. But what is interesting is that I could re-implement it using coroutines. And a number of languages, increasing number of languages support coroutines, which is a great idea from the 1950s that's coming back. And what's interesting about this is it gets us thinking that historically, people have always tried to do things by throwing threads at problems, and certainly multi-core processors make that even more tempting. But in many cases, we must also recognize that there is a complexity and a lack of necessity in many cases, that sometimes we're at the wrong level. Sometimes a coroutine solution is more elegant because it is easier to reason about. You can express time quite adequately in this, but coroutines have the benefit that there is only ever one thread actually executing. The concurrency exists in concurrent activations of possibilities. This is one thing that objects give us, but coroutines give us more directly. That is a kind of a profoundly useful observation, but it also makes incredibly good use of linear time. Sometimes a thread solution can actually be less efficient than a coroutine-based solution for reasons of scheduling and locking. This is also in some ways simpler to implement. Another way of looking at this problem is to recognize that it could be an event-driven problem based on time. It's all about time. This is an event-driven problem based on time. And so I can use an event-driven style as well. Now, what we've just done in a few lines of code is actually have a discussion about architectural style. There are a number of architectural styles that we can adopt, and each of them has different trade-offs in terms of performance, maintainability, and so on. And we can demonstrate that just by looking at the smallest detail and explore that. We don't always have to go to the largest level of detail to find the question or the answer to our questions. So Will Gompertz, in a rather nice book called Think Like an Artist, he's kind of inviting us when we are dealing with architecture. He's talking specifically about art, but I find the same is true in software. We're talking about a very specific mindset that is crucial when it comes to the act of creating. It is an attitude that can be encapsulated in a simple but demanding rule. Always think both big picture and fine detail. Thank you very much. Let's stop there. There's a lot more that I could say, but that seems that's a nice conclusion. So
Kevlin, yeah, I mean, your last slide, the last message, I mean, keeps me thinking. So big picture and fine detail at the same time. How do you train this? How do you develop this skill?
That's a really good question. There is a paper that was published a few years ago that I've not yet finished reading because it's quite long. It comes from the early 1990s, and I was put onto it by it's referenced in let me think, in Lean Software Development by Mary and Tom Poppendick, and they talk about the idea of when actually observing how people work. And it turns out that they show people how people solve a problem over a period of a few minutes. And it turns out they're going high level, low level, mid level, and they're constantly doing this over a matter of minutes and hours, where sometimes we think historically when people talk about development, they say, oh no, you should only worry about the big things. And then over weeks and months, you descend to the detail. And it looks brilliant when you put it on a project plan, or when you present it as here's how we're going to do the project, or this is what this meeting is going to focus on. There's only one problem. That's not how people work. That's not how humans work. We naturally flip between the details. So the first thing, to answer your question, how do we train this? The first thing is to recognize we already have it within us. But we can get better. We can specifically acknowledge this. But the first thing is to say, hey, we do this already. Let's just get better at doing it. The second thing is to, as it were, almost give yourself timeouts. And sometimes you can do it for yourself, but this is one of the potential benefits of working with a group of people, is that other people can move you out of that. The thing we're really bad at is getting stuck at one level as a group. We can end up getting distracted and always, we're supposed to be talking big picture. And then we picked on a detail, and then we got stuck on that detail for the next 90 minutes. And it's just like, okay, we're not moving. The idea is to keep changing between these. In other words, And now what does that look like if I stand back from it? And sometimes this is this idea that you either take breaks or you move around a group, or you just simply remind yourself. It's just like, okay, that's some code. Now, what does that mean in the long term? Take a step back. We have to kind of remind ourselves to do it, because otherwise we do get stuck at one level, and that's where our thinking runs out, and that's where we get a little bit too specific. So if you like, there's a balancing act. What we need to get better is not actually doing it, but balancing these things. And that's what Gompers is pointing out. It is a demanding rule. It requires a lot of you, because the temptation is either you lose focus all the time, you never spend long enough at the right level, or you get stuck on one level. And so what he's saying is, it's got to be down the middle. You've got to be thinking, oh yeah, what does this look like in code? Oh, that's great, big picture. But how you're talking, there's an interface, maybe you use the lollipop notation for an interface, you put it on a whiteboard. What would that interface look like? Show me some code, share a screen. And actually, I had this positive experience with a team before recognizing that this was actually a good thing formally, that what we would often have in the room is we'd have always a screen being shared, but also a whiteboard. And then sometimes we go like, well, hang on, wait a minute, what does that mean? If I'm writing code, this all sounds great. And obviously it works on the whiteboard. I've never seen anything crash on a whiteboard. It always works when I draw it up there, but show me the detail. And that can sometimes raise questions of like, what types are you using there? What are you assuming there? Or are you making it up? I thought we were using a different protocol. In other words, that's where some of the important questions come out. And then you go back and you sort of say, okay, let's look at it from this point of view. So the training is really a training of awareness and doing it. Yeah.
Yeah, absolutely. I mean, it's amazing for people who had internally this, discipline but otherwise, I've found it very useful to work in pairs, with a colleague or a mentor or someone who, points exactly, look, you're for 2 hours, you're too high level. And then you're stuck with one very particular low level thing, and you don't do the dance correctly.
Yeah, exactly. And as you said, dance, that's a perfect way to capture it. What we're trying to do is get better at choreography and our movement. Okay, it's easy to
get inspiration, right?
So inspiration. Here we go, the performing arts again. The point there is that you're trying to find what is the movement what is the movement that is movement, so you don't stand away from the dance, never getting involved, but also you don't want to tread on everybody's toes. You've got to work with other people. How does this work? And then to recognize when a change is appropriate. So actually there's quite a lot you can get out of that metaphor. Yeah.
Mm-hmm. I think tango is a good example for the right dance.
Yes.
For this.
Yeah. That tango is a thing that kind of like my wife and I have been threatening. One day we will try it, and we've been saying that for I don't know, about 20 years. Maybe that'll happen one day. But we, I don't think we. I think we grew up in the wrong generation. We're kind of like into rock stuff. But yeah.
Someone was asking what the name of the paper is, and think.
Let me
see. That is covered already. Lean software development book or something.
I got it from the Lean Software Development book, but I might even have it. Let me just see if I've got it in my. No, I don't think I have. I'm just trying to see if I actually have it. Wait a minute. I do think I have it. Yes, I do have it. No, I don't. My mistake.
No worries. We could leave it on the.
Oh no, I've got it. Right,
later
yes.
on. Not a problem.
It is. It's called. So wait a minute. Are we still sharing a screen? Good.
Yes,
so let me just pull this one out, and I will. Let's just. Okay. The paper is Designing the Design Process, Exploiting Opportunistic Thoughts. Okay, by Raymond Guindon, and you can just find that. And in fact, so if I just go through, I might even be able to find the diagram or one of the initial diagrams. There we go. We see in a problem solution over a period of minutes, the scenario view, the requirements, the high-level solution, medium-level solution, low-level solution. And we see that over a period of minutes, people are moving naturally between these different levels. And that's a very natural way that people address that. So I have only skim-read this paper, so I can't make strong claims about it, but I came across it in the Lean Software Development book. But if you go back to that, if you actually want to go and read it for yourself, Designing the Design Process, Exploiting Opportunistic Thoughts by Raymond Guindon.
Excellent. I mean, looks like a very good tango book.
Yeah.
So let's do the tango, right?
Yeah, I think I'm way closer to reading this book than actually.
Who knows then? You know, I mean, you could get inspired and start doing the tango from this architecture book. So no, goes by.
Let's see how it plays out. Let's start
both
with
ways.
the architecture book first.
Okay.
Yeah. Now there's a couple of questions in the threads which might be worth me answering now, I guess, if we have time.
Yeah, we have a couple of minutes. I mean, I think we can.
Yeah. Okay. So there's a couple of observations. What about testing? Testing cases should only be specific. Start with what you know. Start with where you are. Test generalization is an important step. But the problem is that sometimes people jump into writing general tests and they end up with complex tests that are actually difficult to understand. The tests are not habitable. So in other words, start from where you are. I want to, and of course we can be too specific about things. Sometimes people can make a test about one piece of data, whereas actually we want to extract what is the general property of this. And our specifics are our examples. And what we're looking for, again, is there's a dance here to try and find the right level. Whereas sometimes people write just like, let me just put it this way: the way to test sorting is not the way that I showed on the slides. It's more complex than that. But what people often do is they end up with one big complex test and a large amount of data, and then is this all sorted? And it's like, actually, that's not very helpful, and it often misses certain very important cases. So the idea is you're trying to find this balance. You're moving from, I have a specific example, but I want to understand what it is generally trying to prove. And I may use through data parameterization or property-based testing, I may be able to generalize it at that level. Now, there's another question here that is also about security, which I think is interesting. Security is a constant concern. There's a whole, but you're never done with security. It's open-ended. And therefore needs to be part of an ongoing process. And sometimes that will give you feedback that there is something fundamentally flawed in your architecture. But what security does, I like the end of the question, does this relate to technical debt in your view? Yes, it does. I'm so glad that somebody else has seen this. So yes, Andrei Nikolai, that's perfect. There's an interesting thing is that many security issues come from the vulnerabilities of the pieces of code that we depend on and the other software systems we depend on. So we compose larger software systems out of smaller systems, and we often get these are reused in various ways. The problem is that for many people, they don't know what their system is built of. They say, I don't actually know what our architecture is because we're using other stuff, or there's this piece of legacy code and we don't really understand it. Now, let's look at that from a security perspective. We're either dealing with dependencies we don't understand, or within our code, dependencies on legacy code, unmanaged technical debt. And I'm going to make a distinction here, but there's a different conversation. That my blog post on the exactitude of technical debt goes into it in more detail. If your technical debt is unmanaged, it basically means we don't know what we've got and we don't know how it works. That's what you're saying. Now, I want you to say that, stand up in front of a group of people and say, yes, our system is secure. We have no idea how it works. Those two statements do not live in the same sentence. It turns out that if you care about security, it means you must be managing your technical debt. You cannot simultaneously say, we've got loads of unmanaged technical debt, but damn, we are secure. You can't make those two statements because the second one disproves the first. You're making claims about things you do not yet know. So yeah, there is a relationship there and very few people see it. It's an important one. Okay, so I think that is everything answered. Yes, it is.
Yes. And we're just in time for the next session. So before we get into that, Kevlin, thanks a lot again.
Hey, guys, thank you very much.